All right, I guess we can get started. I see some familiar names. Um, if you haven't had me before, my name is Brian. Uh, I work in condensed matter physics lab with Young Tao Sui, um, and I'm going to be the TA for the course. Just a few things to get out of the way. I'm sure it's on iLearn, but I'll put my email up. Those are zeros, not O's, and that is a horrible looking 5. Yeah, you can email me questions about homework, questions about stuff in lectures, stuff. Any questions related to the course, you can email me. That's fine. And typically, the discussions we try to steer away from questions about homework and keep those in office hours. It all depends though, because Professor Shi is providing the material that he wants done in discussion. So if it's something that can be done particularly quickly and there's some time left over, yeah, we can probably talk about homework and stuff like that then. But yeah, we typically try to keep it to whatever it is he's planned for me to go over. Office hours are same day. It's Fridays, 1 p.m. So you have, I think that puts it all on one day, right? You have discussion at 10 a.m., office hours at 1 p.m., then lectures at like 3 or 4, I think. That's subject to change. If people are emailing me saying like that's a really inconvenient time, can we change that? Then yeah, obviously change it, because the point is for it to be a convenient time for people. Oddly enough, I'm not used to this in an upper division class, discussion is a part of your final score in this class. It's an attendance score though. You show up, you get credit for that day, and I think it's 10% of the total grade. Submitting homework. So I initially put on iLearn that I prefer all the homework to be submitted to iLearn, and I was in a like physics 2 series mindset when I was saying that. So I'm like, yeah, it's usually like 1 page of homework and it's like very uniform and stuff. I can still provide a link on iLearn if that's convenient for everybody, but it's probably more convenient for all of you to just email me the homework, and that's fine, because the multi-page support for homework on iLearn is not great. It's very inconvenient. It's a lot easier if I can just open it in my email. But yeah, whatever way you can get it to me. Email should be the easiest, but if there's some dark horse option that I haven't thought of that's more convenient, go ahead and let me know about it and give that a shot. Just as I don't know what his homework deadlines are, but he does seem to have a pretty strict late homework policy. So will be wanting me to stick to that. All right. Yeah, I guess I just had the whiteboard shared just to show my email address. I have a sheet here to share that he provided, because we're talking about crystal axes and what Miller indices, crystal axes. I guess that's it. That's the 2 things to say. It's in 2D. So 2D actually, it's not one of those things where you do in a lot of classes like, oh, 2D doesn't matter, we have to move it into 3D. Especially with more recent being like the last 15 years, maybe 20 years of physics. 2D has just as much merit as 3D condensed matter. But yeah, you will eventually have problems where you have to do this in 3D. So the main idea here is that he wants us to be able to talk about the crystal directions using the crystal as like the crystal lattice as our basis instead of just a grid. Now he made this just a 2x2 grid, but we'll get into how it can be different. This is really, it's just an exercise in treating the crystal as a grid and moving from plane indices to vector indices and knowing what the relationship between those are. So what we have is this 2x2 crystal. It is perfectly square, it seems. He's got some notes on it up on the top of it here. Okay, yeah, just giving the basics of it. Okay. So the first thing he asks is to draw the crystal direction 3, 0. And then then he wants to express it by the primitive lattice vector A1 and A2. That's interesting. I had it as a Word document and then saved it as a PDF. And it was given to me as a Word document, and the Word document was riddled with like poor translation errors from PDF to Word document, but it preserved them. They came back because I read it as primitive lattice vector and dot. And I had no idea what he was asking. So now I'm seeing what it is. All right. So if we treat this like a grid, right? Let's just put some arrows up. This will just make it a little bit easier for us, right? I mean, I know he's got them written here, A1 and A2, but it's a big grid to work with. Any guesses on how it would go? If you want to think back
to the right.
Yeah, exactly. If you think back to just original Cartesian coordinates, think of X and Y, right? That's what's going on here. You're going 3 units to the right and 0 units left. Right? You can start anywhere. I guess actually he gave an origin, so let's start on that origin. All right. So the important thing here is express it as the primitive lattice vectors A1 and A2, which this is again going to look super familiar, right? This is going to be 3A1 plus 0 A2. Make sense? If it doesn't, you can chime in. If you're not comfortable chiming in during discussion, you can always email me. In fact, you can even use like the text chat thing and send a private message. I understand sometimes it's not everybody's okay with just sort of speaking out loud in discussion. So I'll try to cover all communication methods. But yeah, basically this is translating exactly the same way it does if we're talking about X hat and Y hat on just a 2D grid, because he's made it a perfectly square grid. A1 is X hat, A2 is Y hat, and that's how it's going to be following for these, right? So then we have 0, -1. I'll keep the red for this one, and then I'll change colors for maybe the next one. 0, -1, right? Let's do this one in reverse. Let's write this one. So let me get this guy here. This is 3A1 plus 0A2. That would make this one 0A1 minus A2, right? Because it's plus minus 1. So that just has us going there, right? And now I'm not being consistent with the notation here, but there we go. Cool. So we moved 0 in the A1 direction and -1 in the A2 direction. And then, as expected, we're going to combine these two. We're going to move 3 in the A1 direction, -1 in the A2 direction. Which is going to bring us there. And of course, it's going to be written as 3A1 minus A2. Okay. Slightly more interesting problems. I'm going to have to scroll down just a bit, and that messes up all my, there we go. Try to line them back up. Okay. So now we are talking about moving from crystal directions, crystal planes to Miller indices, and I don't think we do the vice versa. I think we just do crystal planes to Miller indices. Move these guys up just off to the side there. There we go. Okay. So now we want to draw crystal planes, 0, 1, 1, 0, 1, 1, 0, 2, and 1, 2, and 3, minus 1. There's some different ways to sort of think about these, right? The way I usually think about them is you just think about which one is, you just think about what's perpendicular, right? I seem to have lost my thing here. There we go. Right, so for example, let's take a look at, and now I'm a little confused with this thing just sitting here. Move everything or nothing up. That's what I should do. Okay. Crystal plane 0, 1. Now I'm going to change the color so I don't get confused with the first one here. 0, 1 would be a vector if it started from the origin. Oh, no, just a straight line, I'm not an arrow. One from the origin, it would point straight up, right? But we're not looking for the vector 0, 1. We're looking for the crystal plane 0, 1. So the crystal plane 0, 1 is the plane that has the normal vector of 0, 1. And this might be a bad example. You'll see why. Because it's not just take these indices and then say, oh, then the vector that's perpendicular is spelled the same way. It's actually, if they are indices A, B, then your plane is perpendicular to the vector 1 over A, 1 over B, right? So if it's 0, just keep it 0. Don't say 1 over 0, just keep it 0. And, of course, 1 over 1 is still 1. So it works the same way for 1, 0. 1, 0 would be pointing directly to the right. So we'd have a crystal plane that's perpendicular to a vector pointing directly to the right. Okay, so this is, here's our crystal plane 0, 1. Here's our crystal plane 1, 0. 1, 1, that's a 45-degree angle, right? The vector's pointing diagonally up. So we want crystal plane perpendicular to that. It all seems pretty straightforward, right? And then we get to the ones that are multiples of those. What about 0, 2? You think, well, isn't 0, 2 just same as 0, 1? It's got the same direction for the vector. It's about the spacing of the planes, right? Because when you draw crystal plane 0, 1, the convention is to draw it at the origin and say that's crystal plane 0, 1, but it actually encompasses a family of, or a group of crystal planes, right? All perpendicular to each other. So if you just went down and spaced them evenly at 1 unit each, that is the 0, 1 group of crystal planes. So for the 0, 2 group, the vector we're talking about that is perpendicular to it is 0, 1/2 now, right? Because you have to do the 1 over 2. So that actually introduces more planes in between each of these, probably straighter and more evenly spaced than I'm drawing. I hope I'm illustrating what it's supposed to look like through my words. So that's the interesting thing, right? The grouping of the 0, 2 planes, they're more closely spaced, more packed together. They're not equivalent to the 0, 1. So 0, 2 crystal plane is not equivalent to 0, 1 crystal plane, but the family or group, I keep saying family, I don't think that's the word used. The group of crystal planes represented by 0, 2 contains the group of crystal planes represented by 0, 1, right? Because if you think of it this way, this is written as the crystal planes that are perpendicular to the parallel to the A1 axis and exist at half integer multiples of A2. So every even half integer multiple, you're getting the 0, 1 as well. I'm going to erase a few of these to give myself some room. leave that. Leave the worst 0, 2, 1 that I drew. Of course, that's pretty typical of me. Right, so this is going to follow pretty similarly then, right? We have the 1, 2 axis, the 1, 2 plane, which means it's going to have, I'm going to change colors to purple here. It's going to have a normal vector of 1, 1/2, right? Because 1 over 1 and 1 over 2. So you can think of that as, if it's 1, 1/2, it might be easier to do 2 and 1 and then just sort of cut it in half. But there's our 1, 1/2. And now this one might be a little trickier, right? Okay, well, so how do I draw this plane then? Okay, so when you're given the indices and it's a little more complicated than just a straight line, you want to think about where it's going to intercept on the crystal axes, right? So we're looking at 1, 2. And if the plane is perpendicular or has the normal vector 1, 1/2, then it also is on its own axes going to intercept at 1, 1/2. And that's made it a little easier for us here, the fact that these are straight up, just a regular 2x2 grid, right? So let's take a look at our origin. We have 1, we move over 1, and then 1/2, it's up this way, right? So it's going to intercept the A1 axis at 1, and it's going to intercept the A2 axis at 1/2. I think I have that right. Oh, yeah. Hold on just a second. I'm losing my pen. All right, and then I want to make it purple again. You'd think I'd be used to Zoom by now. Okay. So it should look something like, I'm gonna get this vector out of here because I'm pretty sure I made a mistake with that. I'm gonna get this at the origin. Okay, so that's looking right. Intercepting the A1 axis at 1, intercepting the A2 axis at 1/2. Yeah. Okay, and then our 3 minus 1. We're going to do the intercept way again too. It's going to intercept at 1/3 on the A1 axis. It's going to intercept at -1 on the A2 axis. I just already circled it in purple. Let's do a different one. There we go, green, 3 minus 1. So intercepting here 3, sorry, at 1/3, and intercepting there at -1. So that's going to look something like that. If I had to scroll down enough for me to get to that third dot up there, it would be a little more perfect. But yeah. All right, so drawing them is pretty straightforward, right? You're looking at the numbers, you're taking reciprocals, you're treating them as the intercepts for the planes, and you can get normal vectors from those two. The last two are sort of, I guess, the more interesting aspects of the vectors, right? So I kind of already talked about number 5 here. It says compare the sets of planes 0, 1 and 0, 2, and are they the same? They're not the same, but the set of planes in 0, 2, or the set of planes represented by 0, 2 contains the set of planes represented by 0, 1. And of course, if there was like, you know, a 0, 4, then 0, 4 would contain the 0, 2 planes as well as the 0, 1 planes. A 0, 3 would not contain all of 0, 2, but it would still contain all of 0, 1, and so on and so forth. Okay. The last bit, and this is, I've sort of been talking about this the whole time too, I guess. What color haven't I used? Yellow? There we go. Compare 3 minus 1, the vector, the crystal direction, and 3 minus 1, the crystal plane, right? So we drew 3 minus 1, crystal plane. That's this green one here. So actually, let me just stay with green then. And let's draw a vector 3 minus 1 from one of the endpoints, right? Do it like that. And that kind of really gives away what the answer is. But I think we already knew the answer, right? Just extend that plane there. Okay. So what's the relationship between, and I've been mentioning this too while I was drawing them out, the vector with the indices 3 minus 1 and the crystal plane with the indices 3 minus 1. The relationship between them is that they're perpendicular to each other, right? Because that's when you're given a crystal plane, you can look at it 2 ways. You can say, all right, let me take the reciprocal of each number, and those are the intercepts of this plane. Or you can say, let me just look at that as a vector and say, I'm looking at the plane that's perpendicular to that vector. So then if they ask you, what about a vector that looks like that and a plane that looks like that, well, they're perpendicular to each other. That's the relationship between them.
I have a question.
Yeah.
So you know how we show this the set of planes contained in like the 0, 1 set and that sort of thing?
Yeah.
Can we have like the plane 3 minus 1? Can that be a set too?
Yeah. Yeah, and that would be a pretty that would be like more tightly spaced than say like a 1 minus 1 or something. But yeah. So I guess let me try to think of it this way. So for your example, like a 3 minus 1, let me grab orange here, right? 3 minus 1 would intercept it 1/3, and minus 1. Oh yeah, so that's the guy that we have there. So he would intercept it every like 1/3 interval and every minus 1 interval, right? So maybe I'm not drawing that perfectly well, but so here's like 1/3 on the A1 axis, here's 2/3, and here's 3/3. So there's 3 intercepts along 1 unit of the A1 axis, and then down the A2 axis, it intercepts at -1, -2, and -3. So that's what you'd want to interpret from like what the set of the planes is then. So in that example, if we had a set of planes that's 3 minus 1, then yeah, I mean that's a perfectly valid set of planes. And what it means is that this is how those planes are spaced out then, that along 1 unit of, say, it's best probably to think of it in like 1 direction at a time. In say 1 unit along the A1 axis, you should have 3 intercepts from that set of planes because they intercept at 1/3 intervals. And then along the A2 axis, you should have a 1-to-1 because it intercepts at -1. But yeah, that's a perfectly valid set of planes.
Okay, Thank you.
No problem. Now, the note that he makes to the TA on this is that basically like what we're supposed to get out of this, which I kind of explained, just like moving from indices to planes and from planes to indices, and what the relationship between the vectors and the planes are, and what a set of planes means. Then he adds, if they can do it in 2D, it should be pretty easy to do it in 3D. And I get what he's saying. And I guess this is depending on how you learn to talk, and like where you learn your different definitions of your language from. To me, that's a difference between the definitions of the words easy and simple. And that's why like I first read, oh, it should be easy, and I'm like, no. It is simple. It is just this simple to do it in 3D. But the complication of having to do that one extra dimension makes it a little less easy or a little more complicated. So I will agree with him that moving on to 3D, it's the same steps, so the simplicity is the same, but the fact that it's compounded by a third dimension, it's going to make it a little more difficult. So don't get discouraged when you get to 3D and you might hear, I don't know how he would be in office hours. Maybe if you hear him say like, oh, it should be easy to move to 3D, I think what he's saying is that like the steps are exactly the same, but it should obviously get a little more difficult since you have to do more things. Just that little note there. That is, surprisingly, that is all he wanted to go over for the first discussion. It's just this one grid and these 6 questions about the grid. Those first 3, I guess, to kind of like do an easy intro into it, just first 3 just sort of drawing vectors on a 2D grid. One way this could have become not super difficult, but a little more complicated is, let me, so it's going to draw another grid over the existing grid. That's probably not the best thing to do. Let me go to whiteboard here. One way he could have complicated it, and this is actually the more common thing that you would see, is maybe he could have distorted those vectors, right? Instead of having something that looked like a Cartesian grid, maybe he could have had the A1 and the A2 vectors look more like this, right? And then we could have built a lattice out of that, right? Or sorry, we could have built a crystal out of that. I'm also not great at using the correct terms for stuff, which is unfortunate because it's kind of important in physics, believe it or not. I'm not going to go and draw the whole thing. I'm just going to give a brief example. I'll stretch this one out. There we go. The same concept would apply here, right? If we wanted to draw on here, let me go to red. I shouldn't have drawn arrows for this. I should have just made them lines. But anyway, if we wanted to draw, like, say, vector 2, 1, and this origin is the bottom left here, it would be the same thing. We'd move 2 along A1 and 1 along A2. 1, 1 would be obviously not perfectly like the regular Cartesian grid, but the same concept would apply. And then when we got to the crystal planes, the same concept of, it's how many units along that crystal axis when you're thinking of the intercepts, right? So if we had a 1, 1 plane, a 1, 1 plane would look like that. If we had let me go to purple, and we had, let's say, a 1, 2 plane. Our 1, 2 plane would look like that. So the concepts are the same, and that would just be one way to sort of complicated, is making it not a perfectly orthogonal, like 90-degree angle grid. And of course, when you introduce third dimension, it can get a little more complicated. More often than not, and it's not always perfect. And in fact, in practice, when you're looking at real crystals and stuff, there's the more interesting materials, it's not usually perfect this way. More often than not, the third axis is just like your z-axis in Cartesian coordinates. It's just coming straight out of the page. You draw the 2D one, and then have the third one come straight out.
A question about something you said earlier.
Yeah.
So for the crystal planes and crystal directions, if you have the same coordinates for both, you mentioned that they were orthogonal, or I think your example was that green crystal plane and the green direction.
Right.
And is that only the case in the orthogonal, I don't know what you would call it, in the situation where like it's just a square grid? So like, would that still be the case in this setup?
It should be. Let me see for an example here. That was 1, 2, and then this would be 1 1/2. I mean, just in practice right now, it's looking like that's not exactly the case. But also, I'm prone to making mistakes on the fly. It should follow through. And if it's not, like, so the thing is, when you change the grid to be like this, what you do is you make a change of basis, right? So when you do this change of basis on a picture, right, we're not making a 90-degree angle from A1 to A2. But when you make, say, like state vectors that represent things on this grid, or when you make basically just when you make your basis out for it, the idea is that you are going to work in a space where those are considered orthogonal to each other. So that's another reason why there's so many words for perpendicular, is because they come about from these pretty specific cases where we want to say orthogonal and not perpendicular and not normal, because geometrically they're not normal or perpendicular to each other. But in the system and in the space that we're working in, because those are the two base vectors, they're orthogonal to each other. I wish I prepared a better explanation for that. It's a good question, though. So I guess, yeah, that's probably the best explanation I can come up with on the fly for it. I'll have a more eloquent answer when I have some time to sort of gather thoughts on it. But that's kind of the gist of it, right? Yeah.
You would think it's just because you're making a basis out of it, like you said. So you need the base indices, and given that they're linearly independent of each other in for this specific system.
Right. So like you can't end up anywhere on A2 traveling on A1. Right. So yeah, that's like exactly what you were saying. I was just trying to think of my dumber way of saying it. Yeah, but what I mean by a better response is I'll collect like examples to sort of illustrate it and be able to talk about it better then. But yeah, that was a good clarification though, because you're making those the base vectors, because they are the vectors that make up the basis. It's kind of like the definition that they're going to be orthogonal in that space.
What was the question?
The question was, so on our regular like 90-degree angle grid, the like 3-1 vector and the 3-1 plane, the relationship is that they're perpendicular to each other. And does that hold true on grids that are not, like that the base vectors are not beginning as perpendicular to each other? And if we just did, we can try to draw it out just to do a quick one to give a good illustration of it, right? Of course, the other question is, how good is my grid? Probably not very good. And let's take this bottom left to be the origin, and let's go with 2, 1, right? So then the 2, 1 plane would be the plane that intercepts at 1/2 and 1. I have freehand on. I don't want freehand. Right, so that's the illustration of it not appearing to be a perfectly right angle, right? This is the 2, 1 versus the 2, 1. Yeah, I'll come up with some examples for that to sort of illustrate it better, because that is an important thing. I hadn't thought of it to bring up. I wish I did, because it'd be good to have those examples today. But yeah, that was a good question.
Hi, can you hear me? I have a question.
Yeah.
In that case, how can we draw the plan like 1, 0? Because in the square grid, we know it's perpendicular, but in that case, it's not perpendicular like that one. So how can we draw the plan 1, 0?
Right. So let's let me change colors here. So 1, 0, the vector would look like that, right? So the 1, 0. Oh wait, sorry, that's 0, 1. Is it gonna let me spin it? There we go. There we go. So there's our 1, 0 vector. So 1, 0 planes should just be the planes that run along the A2 axis, and intercept at intervals of 1 along the A1 axis. Let me write it out, because 1, 0 is our vector. So then the 1, 0 planes. Okay, this is the 1, 0 vector. Okay, that might be muddying it up if I'm drawing arrows everywhere. So the 1, 0 vector is the vector there, and the 1, 0 planes are then these planes that in this basis are orthogonal to that vector, and that intercept the A1 axis at every 1 unit along that A1 axis.
I understand. Thank you.
But yeah, so yeah, that's an example of, that's actually probably a better illustrative example than me trying to do the 2, 1 over here. Yeah, so that kind of is like plain a day in your face, showing that like these planes geometrically are not going to be perpendicular to that vector, but in the basis, they're orthogonal to that vector, or that vector is normal to that plane. So when the basis is changed that way, I guess the best way to think about it is to have, I mean, it might sound silly to say it because this is sort of like implied when you look at any normal 2D grid. It's to have those base vectors in mind when you're thinking about what's perpendicular, what's orthogonal. I lost my cursor again. Okay, there we go. Right, so if you just carried around this little origin of these two base vectors, and I'm trying to select them without selecting the line that I have there. Okay, yeah, there we go. You can bring them to each little point that you're trying to examine to see if something's normal. Obviously, you're not going to do this in practice. You're not going to actually like grab like two vectors and move them around. But like we clarified earlier about it, the base vectors make up what is orthogonal, right? So when you have A1 and A2, now when you want to draw something perpendicular to something in this basis, orthogonal to something in this basis, that's the reference. This is what two orthogonal vectors look like in this basis then. All right, I think that covers it with a little added complication there of distorting the grid. The last bit, which I'm not going to try to draw on Zoom, is it's actually a pretty common one, so maybe it would be worth drawing. I don't know. I'll try to have an image of it for next discussion. As you may or may not know, graphene is famously a hexagonal lattice, which I guess there's some debate over the use of that word. Try to get a poorly drawn hexagon here. There we go. Doesn't let me copy and paste. That would be great. No, it doesn't. I'm sure there's some way to do it. Anyway, so yeah, there's some debate over the use of the word hexagonal lattice because a lot of people take a hexagonal lattice to mean a special case of a triangular lattice, like that, and that's not what graphene is. Graphene is hexagonal. And you can think of it as with a basis of two atoms. So that's another way it can get complicated, right? So typically these vectors that you'd use in the basis for graphene would be like this, right? This would be your A2 and this would be your A1. But anyway, yeah, this is sort of just a preview, getting a little ahead of ourselves on it, but just giving a preview of things that'll probably be touched on before the end of the course, especially since Professor Shi does like a lot of work with graphene. He has a lot of experience in it. He's one of the experts in it. I'm sure he's gonna find, and it's also an important topic. So it's something that's worth putting into a course like this. So I'm sure he's gonna have a lot of good examples for that. All right, yeah. So I guess sort of a brief first discussion. Maybe it's just like a dipping the toes in or something like that. He's releasing the discussion material to me like week by week, the day before the discussion happens. So I don't have a pretty good preview of what the rest of the discussion problems are going to be looking like. His description, which I think, given this one, is actually a pretty good description, was that they're in nature going to be like quiz-like questions, but we're just not conducting them like a quiz. We're just going to be going over them together. But they are questions that maybe in another setting, in another class, would actually be utilized as a quiz question. Okay, that's all I've got prepared for today. There's still 5 minutes left. anybody who's had me as a TA before, you know the routine. I have to be here for the next 5 minutes. I'm not going to force you to be here for the next 5 minutes. This is the first discussion. Everybody, like, you never had to do this before because we never had a discussion score before. But now that this one is part of the grade and it's attendance, I'm just going to say first discussion is like a gimme for everybody. I haven't even looked at the list today. It's just, I'm just going to go down the list and give everybody credit for the first discussion. And I'll figure out something for attendance in the future. I think, I mean, you guys are all physics students. Like, you're here in discussion to get an understanding of the stuff. So I think it's probably fine for me to just take attendance in the beginning and then forget about it for the rest of the thing. This isn't it's not a physics 2 course where I have to like trick them into staying for the discussion. So yeah, I'll probably just do that. Just maybe about 10 minutes in, I'll like take note of who's there, to, you know, give everybody time to show up. All right. Yeah.
Yeah, sounds reasonable.
Cool.
I have a question.
Yeah, sure.
When we have the honeycomb lattice where we have the atoms at each of the corners, what exactly is like the base unit of like the actual atoms?
Right. So that is now I got to get my terminology right on this. So that would be it's a hexagonal lattice when you look at it, right? But the way they would describe that, let me try to get it written. Actually, let me just draw it with the
The
dots.
professor drew out like a couple of the honeycombs and then kind of drew like a hexagon kind of around one of the portions.
Yeah, so because of the way the atoms are bonded, we label them as atoms A and B. So it's carbon, but there's 2 carbon atoms bonded in a particular way versus bonded in another way. So it's called having a basis of 2 atoms. And that would be the easiest way to do that is to just take, you know, these 2 here. And if I could draw the entire hexagonal lattice, you can imagine that each of these bars represents a red atom connecting to a red atom connecting to a blue atom, right? All right, I'm confusing myself, so let me get the red atoms drawn in there. There we go. All right, so now in this basis, you have different primitive vectors than you do in the lattice. In this basis, you take this setup of this red and blue connected by that one bond there, and you can slide it either up in this direction to the next iteration of that happening, or straight up in this direction to the next iteration of that happening. Right? So if we just went along the lines connecting, I didn't really space them out, right? And you can imagine there's another one up here too. So now, the actual physical makeup of the graphene is this hexagon, right? But if you think of it as having a basis of 2 atoms, which would be this being the basis, so now this is the single unit that we translate around a grid to recreate the lattice. And that's translating this sort of diagonal direction here and then straight up this way. So those are the 2 ways to look at it. There's like the physical lattice is this honeycomb, I should say, yeah. I mentioned that there's controversy over the name hexagonal lattice, and I never mentioned what the alternative word was, I'm sorry. The alternative word, and the one that I think most people prefer, is the honeycomb lattice. So the lattice itself is honeycomb, but the primitive vectors of the basis are more of this sort of rhomboid, sorry, not rhomboid, that would be 3D, this rhombus structure. Does this sort of look like how he drew it, or did he draw bigger? Because Did you do like bigger hexagons over it?
I mean, it was kind of similar to this, or at least like the lines that kind of went all the way around.
Because the
So, like,
other
the outer-
way
The
is like,
outer,
if you think of the centers
here.
of the hexagons, you kind of get that same pattern if you just go to the center
Yeah.
of each hexagon. I wish I had better drawing tools for Zoom. I mean, I'm sure it's there. I'm sure there's a way to copy and paste. I'm just not seeing it immediately. Yeah, those would be the two most basic ways to look at it that I can think of. Yeah, and graphene will probably show up a lot, which I think there was a recent thing with phys.org. I think they made a pretty good circuit out of graphene recently. I'll have to look into it more. I read the headline and set it aside to read later, and then never did. But yeah. All right. Yeah, I guess that's all the time then. I have office hours today at 1, I think. Let me grab my calendar, make sure that's right. Yeah. Okay. So it's same Zoom room, same password and everything. Just it'll be office hours instead of discussion. All right.
Sorry, I had one last question.
Oh yeah. Go for it.
Do you think that we'll be able to get access to the PDF that you use before class for those of us who like mark up the actual PDF?
You know, that's a good point. Yeah, you know, in the future I'll do that. When he sends me what the sheet is, I'll just upload it to the 002 iLearn page, the discussion iLearn page then.
Awesome. Thank you.
Yeah, no problem. That's a good point. I should do that. All right.
Thank you.
Thank you.
When are you going to post this recording?
Usually shortly after. It depends on. I try to do it immediately, so like it depends on how long it takes Zoom to make the video.
Yeah, no worries. Yeah, we had you for EM Waves, right?
Yeah.